Okay, let us calculate the threshold value of AM system for envelope detectors. Okay, as we saw in the last lecture, if we plot the input SNR gamma versus output SNR for synchronous demodulator, it is a straight line like this passing through the origin. But the moment you try to plot the relation between output SNR in terms of gamma, then it is linear for high SNR. The moment it falls down, then it slowly goes down like this. Now which value should I take? Should I take this point as the threshold point, or should I take this point as a threshold point, or should I take this point as a threshold point? So there is no clear definition. Okay, where should I take the threshold point? Somebody comes and say, okay, no problem, you can take up to this point, it is somewhat closer to the linear curve. Say this is my linear curve and this point is somewhat closer to this linear curve. So I can say both are similar. So there should be some kind of justification such that where should I take the threshold point. Now let us give some definitions and do the calculation accordingly. So what we will do is, we first define the point of threshold in a particular manner and then calculate at what SNR, at what input SNR the point of threshold will occur. See, the x-axis is input SNR. We need to find out at what input SNR the point of threshold will occur. So it's a simple calculation. So let us proceed. So we need to find out gamma threshold. So what is gamma? Gamma is defined by SI by NB. That is our benchmark. Okay. Therefore, this gamma threshold is SI by NB, such that below this you will start seeing significant deviation of the output SNR curve compared to the linear curve. Okay. This portion is linear. So that is a definition. So now we can do this calculation by talking in terms of probabilities. So let me first give some important results and then we will proceed. Now probability density function of noise. Probability density function of noise. We said it is a Gaussian noise, right? Wide band Gaussian noise, that means white Gaussian noise and a narrow band Gaussian noise. Okay, so now how is the noise envelope expressed in terms of the quadrature components? That we already discussed. You have n of t, and this n of t, let me write down like this. It is added with the signal and this is given to the band pass filter, and output is your narrow band noise. This narrow band noise is expressed in terms of NC of t, in terms of in phase component, and quadrature component NS of t sin omega ct. Now what is the envelope of this? En of t is equal to square root of NC square of t plus NS square of t. So this is my envelope. Okay, so this is my narrow band Gaussian noise, and this is also Gaussian, and this guy also Gaussian. Okay, so the two quadrature components are also Gaussian. Now what are we doing in the envelope? We are taking the square root of in phase component plus square of quadrature phase component. That means the sum of the squares of the two Gaussian random variables, like so Gaussian square plus again Gaussian square, and we are taking square root. Okay, so the square root of the sum of two Gaussian random variables, and the resultant random variable is my En of t. So En of t is the resultant variable with the square root of two Gaussian random variables. Now what is the nature of this resultant random variable or resultant process? And this one is generally a Rayleigh distributed, Rayleigh, okay, Rayleigh density function. So given that the density function of both NC of t and NS of t are Gaussian, then your En of t is Rayleigh distributed. So what is the density function for Rayleigh distribution? Again, 0 mean and variance is sigma square. In this one, mean is equal to 0 and variance sigma square is equal to sigma square. So therefore the Rayleigh density function is given by let us write down the in phase component. So NC of alpha is equal to 1 by sigma times root of 2 pi, because this is my variance, e to the minus of here the parameter is alpha, therefore alpha minus 0 the whole square divided by 2 sigma square. That means 1 by sigma times root of 2 pi e to the minus alpha squared by 2 sigma square. This is the in phase component, power probability density function of in phase noise component, PDF of in phase noise component, probability density function. Similarly, I can write down the probability density function for quadrature noise component in the same expression, 1 by sigma times root of 2 pi e to the minus alpha square divided by 2 sigma square. Both of them have 0, both of them are 0 mean and variance is sigma square. And now one can easily show that square of these two Gaussian probability density function becomes En of alpha is equal to alpha divided by sigma squared e to the minus alpha square divided by 2 sigma square, where alpha is greater than 0. Okay, so what is your En? En is the square root of NC square plus NS square. And obviously this NC square plus NS square will be positive always. So therefore this density function should be always defined for alpha greater than 0. Why? What is your En? En is square root of NC square plus NS square of t, right? So this is always positive. Therefore this density function is always defined for positive. That is why this alpha is greater than 0 for your Rayleigh density function. But in this case alpha can take any value. Okay, it can take the value from minus infinity to plus infinity. Frankly speaking, if you want to plot, then it looks like this. This is your PNC of alpha. Similarly, you can have the function like this for your PNS of alpha. Okay, so it has both negative values and positive values. But for a Rayleigh density function, it is only defined I'm sorry, the curve will be slightly like this. So this is my Rayleigh density function. In fact, still it is not that much accurate. It goes very steeply like this. It goes like that. This is my Rayleigh density function. Okay, and sigma square is the noise variance of NC or NS, and that will be the same as the noise variance of your narrowband noise Ni of t. And therefore your sigma square is equal to 2 times NB, because it is a band pass filter. Here we have the bandwidth is minus B2 plus B FC, and this is minus FC, and this is N by 2, and this is N by 2. So therefore your noise variance is equal to 2 NB. Here NB noise power, and here also NB. Basically the variance is nothing but power in the noise process. So it is 2NB. And what is the sigma square? Noise variance of your Ni square of t, Ni of t. And this is same valid for your Nc of t, and this is valid for your Ns of t. Okay, so therefore sigma square is equal to 2NB, and this one is Pen of alpha, and this is my alpha, and this is Rayleigh distribution and Rayleigh density function. And this Rayleigh density function is going to exist only for positive values of alpha. So that is a little bit of background that is needed. Now let us come back to our threshold calculations. So we have to define the threshold. We say that threshold occurs if noise envelope En becomes greater than the carrier amplitude. That's what we said, right? So the noise envelope En of t is greater than A, then what happens? Your system breaks down. Okay, therefore the threshold point will define when En is greater than A. Now this will very rarely occurs in the commercial FM system. So let's say this condition occurs with very, very less probability. Let's say with probability 0.01. Maybe once in a year, maybe a few seconds or few minutes, the noise will take over. Okay, in broadcasting applications, maybe once in a year, maybe 1 minute or a few seconds it will take over. Okay, so the probability is 0.01. Let's say you have 364 or 65 days, and then per day 24 hours, and then per hour is equal to 60 minutes. In that, maybe 2 or 3 minutes the noise will take over. So if you calculate, then it will be very, very less. That is why we assume that this condition occurs in commercial AM system with the probability of 0.01. Okay, and the rest of the time the noise is much smaller than your signal amplitude. So what we are saying is, if the probability of the noise amplitude exceeds the carrier amplitude and becomes that is, the amplitude becomes exceeds the carrier amplitude with the probability 0.01. So that is the point at which we will say that the threshold has started. Okay, and this is like not exact definition, it is an arbitrary definition. Okay, so you can change this, you can take 0.05 or 0.1 or whatever it is if you wish. So depending on the what probability value you fix here, the resultant value of gamma threshold will be different. Okay, so what we are basically saying is that the noise amplitude is greater than the carrier amplitude with this much probability. How much probability? 0.01. And the probability of this event happening, this En greater than A is happening, is 0.01. So that is just you have to arbitrarily fix this probability value 0.01 to calculate the gamma threshold value, and calculate the gamma threshold value accordingly that. So this is calculated based on this 0.01. So that is what you need to calculate. So you have the density function like this, and let's say this point is A. When the noise exceeds this region, this is my region, this is my B suffix En of alpha. So basically what you are saying is, this is your density function your Rayleigh density function, that is basically probability density function, and let's say this point is A. So when this area is 0.01, then what will happen? Your noise envelope is greater than A. So that means the probability of En greater than A, this event occurs with the probability of 0.01. This A can be an arbitrary value, okay, that we don't know, that depends on your transmitter power. If let's say transmitter voltage, let's say 10 volt, then you can use this is 10 volt greater than A. And if transmitter voltage is 100 volt, then it will move further towards the right hand side. Therefore En is greater than 100 volts or millivolt, I don't know, microvolt. So therefore what is this event? How do you calculate? P of En greater than A, which is, you just integrate. Okay, so this point is A to infinity. A to infinity. What is your density function? Alpha by sigma square e to the minus alpha square divided by 2 sigma square. So substitute that value, alpha divided by sigma squared e to the minus alpha square divided by 2 sigma squared and d alpha. Okay, and this is very simple to integrate, and after the integration it will be e to the minus a square by 2 sigma square. This is the left hand side, it is 0.01. Okay, so the left hand side is going to be equal to this probability. So it should be, so the right hand side should be equal to 0.01. And now from this equation you can calculate the corresponding value of A by sigma square. So if you simplify this, A by sigma square is equal to 4.605. And what is my sigma square? Sigma square we already calculated, 2NB. So substitute here, A square by sigma square is 2NB is equal to 4.605. Now what do we want? We want to talk about in terms of the input SNR. What is my input SNR? Input SNR is SI by NB. What is SI in our case? SI is equal to A square plus M square bar divided by 2. Now let us assume that for the sake of simplicity of calculation, M of t is a single tone signal. Single tone signal means cos sin omega t, pure sinusoidal signal. So let us say this is A times cos of omega mt. What is M square of t? This is A square by 2. Okay, for single tone modulation, that is A square by 2. For 100% modulation, M square bar is equal to A square by 2. So therefore your input power becomes A squared plus, that is A square by 2 divided by 2. So this is 3A square by 4. Now SI is equal to 3A square by 4, and you substitute in the gamma. Gamma is equal to SI by NB. So this is 3A square divided by 4NB. Okay, now look at here, A square by, where is it? One second, I have done somewhere mistake. What is that? I'm sorry. Sigma square is equal to 2NB. I'm sorry, here I forgot a 2. This is A by 2 sigma square equal to 4.605. Therefore this becomes 4 times NB. Okay, so A square by 4 NB is equal to 4.605. So a small correction here. So a square by 4nb is equal to 4.605. This gamma is equal to a square by 4nb times 3, and this one is 4.605 times 3. So this is equal to what? You multiply that, then finally you will get 3 4s are 12, 3 6 are 18, so 13.8. So my gamma threshold is equal to 13.8. Okay, so this is consistent with the figure which I gave you a few minutes ago. I said approximately 10 dB. Now we got 13.8. So this is typically how do you, okay, this is typically the way we need to calculate the threshold SNR. Now you can ask me on what basis the value of the probability was given to be 0.01. But I have taken this 0.01 arbitrarily. It is a matter of definition. Okay, you should agree on some definition. Otherwise, at which point it starts is really difficult to say. So in that sense, this 0.01 is the more or less you agree on. Okay, some definition. That's it. So basically, the idea is at what point it starts to breaks down. Say this is my linear portion for synchronous demodulator. Then it is following the linear portion, and at one point it is breaks down. So maybe I can choose either this point or I can choose this point. So instead of that, let me choose the middle point. Okay, so at this point you get away from the linear curve by a significant amount. So up to this point you are following the linear curve. The moment you reach this position, then you are deviating from the linear curve. Okay, you are getting away from the linear curve by significant amount. Okay, so that's how you calculate the threshold value. So that's it about the calculation of threshold value of your AM system with an envelope detector. And I think this brings us to the end of the discussion on noise in amplitude modulation systems. So we discussed all kinds of amplitude modulations like DSBSC, then single sideband modulation SSB, VSB-SC, and then finally AM with carrier. In this we consider two cases. The first one is synchronous demodulation, and then we considered envelope detector. Now some important points, let me summarize here. So as a result of this discussion, the first point is the SNR performance of all synchronous modulation schemes. Okay, one with the carrier are the same. If you take synchronous modulation, the performance is same. Like the performance of SSB is the same as DSBSC is the same as VSB-SC if you use synchronous demodulator. Okay, so the output SNR is the same as the input SNR in the message bandwidth. There will be no difference. Okay, so the performance will be the same as your benchmark. They are all very close in terms of the bandwidth. So that is the first point. The second point is when you have a non-synchronous demodulator using envelope demodulators. Then there is a problem. Okay, you get a performance loss corresponding to the power loss that is embedded or implicit in the use of modulation schemes, because in the AM system we pump carrier also. Because of that, there is a loss in the performance. So it is not surprising us at all, because after all we are sending the power. What is the purpose? To simplify the receiver. So AM with the carrier, in AM with the carrier, not all the power is being used to convey the message signal. Somehow just transmitting the carrier which contains no intelligence of the component. So you get SNR degradation by that factor. And the third message or the third point is again no difference between the performance of synchronous detector and envelope detector. At what condition? As long as the noise is sufficiently low compared to the strength of the signal. So that is the third point. No difference between envelope detector and synchronous detector. When your noise is less than signal. So that is the point that we need to measure. If output SNR degrades as the input SNR degrades, that is not a problem. But if it degrades linearly, we say it degrades gracefully. But that is not happening. The moment you go below a certain value, then you can see the threshold effect. Okay, if the noise is higher than the certain value of the signal, then you can see the threshold phenomenon in the envelope detector, not in the synchronous detector. So the fourth point is threshold effect occurs in envelope detector and not in synchronous demodulator. And the fifth point is the threshold occurs when your noise component is higher than the signal component. So that's all about the noise in AM system. Okay, so probably in the next lecture let me consider one example problem on this. Let me stop here. Thank you very much.